The next derivative rule that we're going to talk about is called the chain rule. And the chain rule is a little bit more complicated. I think it's a little bit trickier than the product rule or the quotient rule. So we're going to take our time with this one. And I actually want to start with a little bit of review from college algebra over something called composite functions. Composite functions. And what these look like is they look like functions inside a function. So oftentimes I'll write them as f of g of x. So you have this function g of x that's inside of the f of x or f of z function here. So all three of these functions that I've listed below here are composite functions. I just want to talk through them here. The first one, my inside function, my g of x, because that's what I want to practice identifying right here, is that g of x. My inside function would be 3x minus 5. That's my inside function. And then it's inside of the squaring function. My outside function would be f of x equals x squared. Over here with the square root function, the inside function is that 4x squared minus 7. That is my g of x. That's my inside function. And then the outside function, f of x, is actually just that square root. So you would be talking about the square root function for your f of x, for your outside function. Last one over here, y equals e to the x squared. My inside function this time is actually just x squared plus 1. So that's my outside function, and then my inside function is actually just that exponential. It would be y equals e to the x. So I do want to practice this. We'll look at a couple more examples down the way here in just a minute. But I want to talk specifically about these types of functions, these composite functions, because that's what the chain rule tells us how to take the derivative of. Some of these, like this first example, we could take the derivative of that. I could rewrite this as 3x minus 5 times 3x minus 5. We talked about that as kind of a workaround for the product rule. So I could either use the product rule on this guy, or I could go and FOIL it out and take the derivative of that. So that one wouldn't be a problem. But what if I have, say, y equals 3x minus 5 to the 100th power? That's not exactly something that you want to simplify. So it would be ideal if we could come up with a way to take the derivative without having to really simplify this or multiply it out. The other two functions that we're looking at here, y equals square root of 4x squared minus 7, is really not a great way we can simplify that. So the only way we could take the derivative, we could fall back on our limit definition, I suppose, but I don't think any of us really want to do that because those problems were long and tedious, and my guess is a lot of us were not big fans of that section. Same thing with y equals e to the x squared plus 1. I can't simplify that very much. I guess I could say y equals e to the x squared times y equals e, but even then I'm still going to have the same problem. There's really not a great way for us to deal with this. And again, I could fall back on the limit definition, but this one's even trickier because I would need properties of y equals e to the x. I would have to use some more advanced properties of that function that we haven't even talked about. So what I want to do here is just practice looking at some composite functions so that in the next video, when we start talking about the chain rule, we're a little bit more comfortable identifying what is our outside function, what is our inside function, things like that. So just a couple quick examples. First up, I have f of z equals negative 2z plus 5, and g of x equals e to the x. First, I want to find f of g of x, and then g of f of z. So f of g of x, one notation that we could use for that, you might have seen this in college algebra. You might have said f composed with g of x. Some students read that as fog, but I always prefer the notation f of g of x. So what this really means is you're going to take g of x, that inside function, and plug it into the outside function f of x. So what's g of x? Well, g of x is e to the x. So this really says f of e to the x. So what this statement is saying is I'm going to take my function f, which is right here. I'm going to take out that variable z anywhere I have it and then replace it with e to the x. So I will have -2 instead of times z. I'm going to plug in my input, which is e to the x, so -2 times e to the x plus 5. And then at the end, if you can simplify it, you would go ahead and do that, but this one doesn't really simplify, so that's as good a place as any to stop. There is f of g of x. So when I look at g composed with f of z here, so here I'm talking about g composed with f of z here, we're talking about g of f of z. So I'm going to take f of z, and I'm going to plug that into my outside function, which is g of x. So, okay, what is f of z? F of z, that's -2z plus 5. So this says g of -2z plus 5. So what does this statement say? This statement says, right here, this says I'm going to take -2z plus 5, and I'm going to plug that in for my variable for g of x, which is just e to the x. So that should look like, instead of e to the x, I'm going to say e to the -2z plus 5. E to the -2z plus 5 power. And then again, if we could simplify that, we would want to do that, but this one doesn't really simplify. That's as good of a place to stop as any. More commonly, though, we'll kind of be going backwards from this example, meaning we're going to start with functions that look like this, and we're going to try to identify what's our inside function and what's our outside function here. So in this next example, there's actually a lot of different possible answers. There's not one right answer. But I think there is kind of one, in air quotes, one best answer here. So I'm going to try to focus on that. So I have a composite function, h of x equals f composed with g of x. I want to find my inside function, g of x, and my outside function, f of z. So my inside function, this will take a little bit of getting used to, but you want to look for like an equation of x. Usually if you have parentheses, those are a really big hint as to what your inside function should be, but in either of these two, I don't have parentheses. So you want to look for a function of x that's inside of another function. I always think about it as the more complicated part of this function. So I look at this, I see x squared minus 4. That to me looks like a good candidate for an inside function. So I'm going to call g of x, my inside function, x squared minus 4. So that's my inside function. My outside function then, which is f of z, I'm going to look at what I started with. So I started with square root of x squared minus 4. I'm simply going to take out what I said g of x was, which was x squared minus 4, and replace it with my variable, which in this case we're going to use z. So rather than square root of x squared minus 4, I'm going to have square root of z. And you should be able to check your answers for all of these if you kind of go back and check this work. If I was to look at f of g of x, here, if I take x squared minus 4, plug that in for z, I should have exactly the same thing that I started with. So yeah, we have the right inside function and outside function. One other thing I want you to be kind of checking for in this, because this is the idea of the chain rule, is we take one function which is really hard to take the derivative of, we break it down into two separate functions that we do know how to take the derivative of. So after identifying that inside function and that outside function, we should be able to take the derivative of g of x, we should be able to take the derivative of f of x, or f of z in this case. And in this case we can. We would just use the power rule on both of these. Over here for part B, I have h of x equals -5 times e to the 0.2x. Oops, let's do that in blue. So I need to start by identifying an inside function. I need to start by identifying a function of x. The only x I see is part of this exponent, 0.2x. So it's really my only choice in this case. So g of x is equal to 0.2x. Meanwhile, f of z, I'm going to look at my starting function, and I'm going to take out this 0.2x and replace it with z. So negative 5 times e to the z power. And again, you should be able to check your answer here. I should be able to take my g of x and plug that in for z, and I should end up with exactly what we started with, which I will let you do that. And again, the last thing I want to check here is I want to check that I can take the derivative of each of these two terms. So for this top part, g of x, derivative of 0.2x, I can just use the power rule. That'll just be 0.2. F of z, derivative of negative 5 e to the z. Derivative, don't worry about that we have a different variable. E to the z is going to behave and have the same derivative just like e to the x. So derivative of negative 5 e to the z will simply just be negative 5 e to the z. So this is going to be a really, really important skill for our next section when we actually start to apply the chain rule. And we're going to start with a general chain rule and then try and break it down into 3 specific cases that make it maybe a little bit easier to use, kind of get some more specific formulas that we can lean on.